Hi everyone, and thank you for joining us for our presentation today. My name is Jeff Hatzel. I'm a Senior Application Specialist at Blue Marble Geographics. Today, in our talk titled Got a Drone Now What?, we'll cover the process of mapping with a UAV. We'll discuss the variety of tools and functions associated with Global Mapper's Pixels to Points photogrammetry tool. This will allow us to use drone-acquired data in a geospatial context. This talk was originally hosted by my colleague David McKittrick. Unfortunately, he was unable to be here today, so I'm fortunate to be joining you now and for the questions after the session. With that, I'll turn it over to David.
Hello everyone, my name is David McKittrick. I'm Outreach and Training Manager at Blue Marble Geographics, a software development company headquartered here in the state of Maine. My presentation, Got a Drone Now What? Mapping with your UAV. We're going to be taking a look at how you can use drone collected data in a geospatial context. Drones are everywhere. You see them in many different industries, many businesses, law enforcement, in building inspection, you name it. We're seeing drones cropping up and performing actions, performing tasks that give you that remote perspective. For those of us in the geospatial industry, we never would have considered this to be a viable tool in our toolkit. But as the cost of this hardware has come down, and probably more importantly, as the development of the accompanying software technology has evolved, we can now see these as a major part of our geospatial toolkit. And indeed, we're finding, our company is finding that companies of every side, agencies, government agencies, even individuals, are now able to collect data on demand. And it effectively eliminates one of the challenges we have in our industry, and that is, where do I get my data? Now you have the means to collect your data. And we're going to see that today in my simulation. I'm actually going to go through the process where we can generate some meaningful data from simple drone collected images. The images themselves there's nothing special. They're just top-down images, as you will see. We're able to process those images into a 3D point cloud, and we're going to go through a little bit of the obligatory technical introduction to kind of describe that process. But most of my presentation is actually going to be based on a hands-on scenario. We're going to actually take a look at a workflow where my goal ultimately within the 30 minutes assigned to me is going to be to generate some contour lines from a source data set, which is essentially drone images. The data we're going to generate is similar to LiDAR. Many of you have used LiDAR. Many of you, I'm sure, are very familiar with LiDAR, a three-dimensional point cloud format. Ultimately, what we will generate through the process I'm going to describe is a 3D point cloud. So structurally, it shares many of the same characteristics as LiDAR. In fact, we can do a lot of the same workflows. We can apply many of the same procedures. However, there are significant differences, and we'll talk about those a little bit as we get into looking at the output that we're going to generate. But once again, ultimately, my goal, I've got a little less than 30 minutes now, is to generate some contours from some drone images. So what are we going to do today? Well, let's just watch our little drone going up in the air first. This is actually one of my colleagues who's now a licensed drone pilot. Likes to go out and play with his toys, obviously. Let's first begin with our objective. I'm going to take a quick look at what are we hoping to achieve today. We'll outline the objective of this. Gosh, my time is going down already. 26 minutes that I have at my disposal. We'll then take a look at the data. We'll actually use some real data. I'm going to drag in from off screen a dialog box to show the source data that we're going to use to perform the construction of our 3D data. And again, it's nothing special. These are simple drone images, as you will see in just a second. The technology that is applied here is called structure from motion. I'll describe a little bit about what that is. We'll not get too technical, but we'll go into we'll talk a little bit about the procedure that's followed for these images to be transformed into essentially a three-dimensional model. Again, we've been talking about the fact that we're generating a point cloud. LiDAR is probably the most common point cloud format that most of you are aware of. You may have heard the word FODAR. I really don't like that term, by the way, but FODAR has been used to describe what we will be generating. It essentially is a shortened version of a photogrammetrically generated point cloud. I don't know, FODAR doesn't really work for me, but we'll compare the two. It's worthwhile looking at some of the distinctions. There are certainly advantages to both, but there are also limitations to both. So we'll take a look at that. When might you decide that FODAR, I use the term loosely, is the technology that's going to work for you, or when do you have to rely or have to actually go out and collect some LiDAR? Most of my presentation, I hope, obviously we'll go through a little bit of the introductory content, but most of my presentation is going to be an actual simulation. We'll take a look at some real data. We'll look at structure from motion in action and go through the process of generating some data. I'm not actually going to do it. Obviously, it would take too long. A little bit like a cooking show. I'll show you the recipe, and then when we're done, we'll show the finished product. I'll pull one out of the oven that I prepared earlier, so to speak. We will analyze that point cloud. We'll go through a few procedures to make this relevant. It's not just a matter of creating a pretty picture. We'll do things like identifying ground points of the points that we generate, which are likely to represent our bare earth, because those are the ones that are going to be important for what we're going to do. We will classify them and ultimately filter them based on that process. We will then generate a DTM, a digital terrain model, from those ground points. And again, my objective is very specific with this data, is to generate some contour lines. So we can reflect, within our 30 minutes, we started with images, we ended up with contour lines. So that is my plan. That is my objective, or my agenda for the next 30 minutes or so. Again, defining the objective, and you're seeing a little bit of a screenshot with some of the data that we're going to be working with, those little icons representing the location where our drone images were captured. My objective is the transformation of overlapping drone collected images into a three-dimensional geospatial model of our target area. That's the goal in this procedure. And this is a workflow that's accessible to anyone now who has the necessary technology, which ultimately is a drone with a camera. Now, the technology, as I mentioned before, is structure from motion. In a few minutes, we're going to take a look at what exactly that is. But before we do, let's take a look at what data we're going to be playing with. What's the source data? Now, from off screen, I'm just going to drag in a window here, and you'll see, if I expand it slightly, a number of images. These are just pictures. They're top-down pictures collected by a drone. I'm just going to double-click to open one up. I get inevitably off screen. I'll drag it into view as well. And you can see it's just a top-down view. These images, as you can see, you might even be able to notice in the way they're structured, have the same content repeated. They overlap. And we'll talk a little bit about the requirements in terms of things like overlap. That's required for the basis of what we're doing. We need to be able to perceive a given location from multiple perspectives. In this building, obviously, you can see an example of that. And we'll see this in action in just a few minutes. The other thing that's important about the image is if I go to the properties of that image, I'm just going to right-click and go to my properties in Windows and specifically go into the details. If we scroll all the way down through all of this information about that particular photograph, you will notice here that it has GPS information. This is what this technology is based on. We know the location that the drone was, where it was when this image was taken. And with that knowledge, applied to all of these photographs, that's how we can determine where every point on this surface is in three-dimensional space. And once again, we'll take a look in a minute at the process of structure from motion and how that actually is applied. So again, a quick snapshot, a quick look at my source data. I believe there's 148 images you'll note here. This is what we're going to process and again, ultimately generate some really cool 3D data. But before we get there, what exactly are we going to be doing here? What is structure from motion? What are we talking about? A very crude little graphic over here on the left side maybe gives you a sort of an illustration. The little squares represent the images collected by your drone. The little dots on the ground, maybe a target point, maybe something that's significant, something that's visible. And the representation here is showing us that we can see those points from our multiple perspectives. So what exactly is structure from motion? Well, it's image analysis when it comes down to it. We're looking at images and we're looking for patterns of pixels in your images. That's ultimately what it is. It's looking for recurring instances. For instance, that building that we just previewed, we're looking at that from multiple perspectives. In order for this to work, the target area needs to have texture or visible structures or visible features, I should say. It will not work with a plain bare ground model. You're just not going to get visible features that can be used for the analysis. So things like a snowfield or a beach or a desert where you have no variation in color or texture, this is simply not going to work. You're not going to be able to generate a usable point cloud. Nor will it work if you're looking at images that have like distant sky view. It can't analyze the sky. You're looking again for colors, for patterns, for recurring patterns. So a top-down model or even an oblique model will work, but when you start to get into a situation where you're not seeing any difference, it's a field for instance, you'll find it will struggle with that type of application. Other considerations here, your drone is obviously flying in multiple directions, and as it flies, it's possible that the underlying terrain is changing in some way. Maybe there's wind that's blowing the leaves, or ripples on a pond, or something of that type, which will significantly change what it sees in the next image, or even shadows based on the sun going behind a cloud, or it happens, somebody walking through the scene, or a vehicle driving along a road. All of those contribute to situations where your data is going to be corrupted, is not going to work. So obviously with those considerations, some initial planning and preparation is essential when you're embarking on this process. But again, we need texture for this to work. Overlap's important as well. Having the visible features in one image is simply not going to work. You have to be able to see them from multiple perspectives for this procedure to work. 60% at least. And you saw in those images we previewed, we were looking at that building several times. So there's significant overlap, certainly sufficient overlap for what we're hoping to achieve. Again, recurring patterns of pixels in adjacent images are identified. A feature that's recognizable, a building, and the procedure will analyze and recognize those recurring patterns. It simply uses a process of triangulation thereafter to determine where that visible surface is in three-dimensional space and will create a point, a single three-dimensional point. Now it repeats that many, many times, obviously, when it detects other structures, other surfaces, other features, and you end up with a very closely spaced three-dimensional point cloud. But the process is simple triangulation. You're looking at a feature from multiple perspectives and a little bit of math under the hood there, and you generate that point cloud. You can also, to ensure the geographic integrity of your data, use ground control. Now, ground control in this context would require you to have either visible features that are captured in your images or even targets that you lay on the ground. It's quite common for you to literally place a target on the ground, survey that location in 3 dimensions, come up with 3-dimensional coordinates that are very precise. Those ground control points then can be used to improve the geographic integrity of your data. Now, it's not required. If you're just developing a model for the model in and of itself, it will still be created without ground control, but obviously for the purpose of geographic integrity, it is important that you have those ground control points. So as I mentioned earlier, there was a kind of overlap between LiDAR and FODAR. They're comparable. The structural characteristics of the output are similar, 3-dimensional point cloud, but there are distinctions. A graphic represented over here on the left side showing an aircraft, and I assume a LiDAR-equipped aircraft, as well as a drone. Obviously, the drone is collecting an image. The LiDAR is collecting data in real time. LiDAR is an active system. Laser-based system that literally scans the ground, picking up returns from a laser pulse, determining where those returns were reflected from, and ultimately generating a point in real time. When you land that aircraft, or when you bring your drone down, because you can obviously have LiDAR on a drone as well, you basically have the data good to go. You can start working with it in real time. Whereas with FODAR, with the photogrammetric point clouds, there's a lot of processing involved. You collect the images, there's a lot of work involved before you can actually do anything meaningful. Both have value, and it does depend on your requirements. It also depends on your budget to a large extent as well. So let's take a quick look at some of those distinctions. Light detecting and ranging, our LiDAR on the left side, our FODAR on the right side. It says it requires flight planning under LiDAR. Reality is you require flight planning for both procedures. And indeed, traditional LiDAR, while it did require a manned aircraft, the technology has become miniaturized to the extent that it is now something you can deploy on a drone as well. So yeah, both would require a certain amount of flight planning. Traditional LiDAR required a fixed wing aircraft and a pilot. So that usually was a little bit more involved, required optimal conditions, etc. Whereas a FODAR collection process, you just need a clear day and send your drone up, and it doesn't obviously require any significant planning. The technology is a laser scanner, obviously, for LiDAR, but for FODAR, you're just looking at a camera. Obviously, the higher the resolution, the better the quality of the image. 20 megapixels is an optimal resolution, and that's off-the-shelf technology. That doesn't require anything significant. Obviously, light detecting and ranging, LiDAR is more expensive. The technology itself is expensive, and FODAR just, again, requires your drone and a camera. The LiDAR will give you in real time, as I mentioned, a clean, sharp, real-time point cloud. You're going to get it immediately, whereas the FODAR process requires you to do a lot of processing to get that data. Now, the final item here is important because when we analyze image, we're analyzing basically what we can see. And if you look from the top down, if there's an area with significant vegetation, you're seeing the top of the canopy. The analysis, the interpolation, the visualization will just be based on that canopy layer. You're not going to get ground, in other words, when you have a lot of trees. Whereas with LiDAR, the LiDAR technology is able to penetrate through even the most dense foliage to give you at least some returns that are ground returns, allowing you to generate a decent DTM or digital terrain model. So depending on your use, depending on your budget, both technologies will ultimately create the same thing. So let's take a look at a very specific process using the images that I just previewed. We're going to throw them into a piece of software and we're going to generate some photogrammetric point cloud data. Now, without getting into too much detail, the software I'm using here is Global Mapper, and some of you may be familiar with it. Specifically, I'm using a component of the LiDAR module, which is a point cloud processing component that's added onto Global Mapper. We're going to be using a tool called Pixels to Points to take the pixels in our images and generate points. So very quickly going through the procedure, I'm not going to dwell on any of the individual steps. First thing I'm going to do from off screen is just drag and drop those images that I previewed, and they will be loaded into the software as picture points. These are little icons representing where the drone was located when each image was captured. We can select them and preview them, again, using whatever your default image viewing application is. You can see each one. You can see it in two-dimensional space. If necessary, we could also see where these are in three-dimensional space. So our images are loaded. The background, by the way, is just a low resolution visual image, just to give us a visual perspective. Again, you can see this farm building that we were looking at previously. The tool itself is very simple. I'm just going to launch Pixels to Points. I'm not going to go into a lot of detail here. Suffice to say, we're going to load the images. We'll add those that are loaded. In other words, we don't have to go to the external files, and it'll give us a preview, a tabular view of all of our images, giving us the details, giving us the coordinate information, giving us the altitude, the relative altitude, giving us the elevation as well. So all of this information is here. We also get preview here, a preview of each of these images. As you can see, you can scroll down and at least get an idea as to what coverage you have, what your images are displaying, etc., etc. Now, if we had ground control points, we could add them here. In this example, I don't have ground control. It's not an issue for what I'm hoping to do. In fact, we do have tools that will allow us to go through a post process to rectify the resulting data, to tie it into an existing ground model, if that's something that we require as a post-process. Obviously, ideally, the ground control points would have been assigned when the data was collected, and we would have seen those visibly on the surface and being able to tag those. Ground control points would be available right here. Now, in this tool, there's a number of settings pertaining to how the data is going to be generated. If we can reduce the resolution if necessary. We can harmonize color to accommodate maybe differences in color with our different flight lines. But ultimately, when we run the process, we're going to generate 3 different files. We're going to generate a point cloud. That's what we're going to be using for the analysis that we're going to be performed, but we'll also, as a byproduct, get an ortho image. Now, the ortho image is essentially a gridded version of the point cloud. It's a rasterized version of the point cloud. Now, in theory, that ortho image, geographically speaking, is going to be correct in geographic space based on the positioning of our point cloud. So it's not just a adjusted version or a stitched version of our individual images. It's a recreated version of a top-down image in a two-dimensional form. We're also going to generate a mesh, again derived from our point cloud. This is probably the eye candy output, and we'll take a look at this in 3D in just a second, but this is going to give us a really nice model of this target area that we're looking at here. Now, I'm not actually going to run through this process. If we did, it would take quite a while, depending on the resolution. It can take upwards of an hour to run through the process. Essentially what it's doing, as we've described, is looking for these recurring patterns within each image and reconstructing that as a point cloud in three-dimensional format. As I mentioned, this is a little bit like a cooking show. So what we're going to do is we're going to take a look at one that was previously prepared. I'm going to save, close the dialog box, and we'll turn off all of these images. I'm just going to select them all. We don't need to see them anymore. Let me highlight them very quickly here, and we will, from off screen, we will drag in the output file. So just 1 second. It's obviously a lot faster than the process of generating it initially. So this file that I'm bringing in actually contains the three outputs. We're seeing them represented in this top-down view. Once again, I want to turn off a few of my underlying layers here. I'm going to turn off the base layer that we were using for our visual reference. So this data you're seeing, again, there's three different files. There's my point cloud. We're going to be spending a little bit of time on that one. Let's take a look at the others first. I'm going to turn off the point cloud and my mesh. Now what we have here is an ortho image. This is a top-down two-dimensional view generated, as I mentioned, by gridding the point cloud. This is a geographically precise top-down view, again derived from the drone images, and again processed through that point cloud. And there's also a mesh. Now the mesh initially will look just like the ortho image, except this is actually a vector file, and it's a vector file with textures. And if I pop up a 3D view here, we will see this a little bit exaggerated. Let me drag this in from off screen just a little bit, and we'll make it slightly larger. Wants to keep moving away from me here. Let me adjust my exaggeration as well, so a little bit too exaggerated here, and we'll click OK. And you can see now this gives us a really nice three-dimensional construction of that area. Now this, again, I'll have to remind you, this reconstruction was generated by analyzing simple top-down images, and the recreation of this in 3 dimensions was based on, again, the point cloud that was generated. This is very cool a visualization of this area now in 3D, and you can get right down here. We can do a flyover, we can record a flyover, things like that. So this is the eye candy, this is the ooh ah stuff. Let's go back to the point cloud itself. Again, this is the source data that's used for all of the other procedures, and we can visualize this in a number of ways. We can visualize this by elevation. Got a strange shader going on here. I'm not sure why my colors are as they are. We can visualize by the intensity. We can visualize by classification. And this is the one I want to look at here, because you can see this is something that I had done previously. We were able to determine within our point cloud which of these points are ground points. And these brown points have been assigned a ground classification. Again, we're moving into the LiDAR world here. LiDAR data natively will have your classifications. Those of you who have worked with LiDAR data will be familiar with those classes. And here we now have 2 classes present. We have a unclassified, such as the building. We can see the classification value here. Never classified as class 0. And if I click on one of the brown points, we can see it's a class 2. This is key here, because now we can remove the points that are not required for our DTM and ultimately generate a raster surface model. I'm going to go through that very quickly here. There's a tool for generating a gridded layer. We'll just confirm the visible layer, that's fine. We're going to generate a binned layer where we want to generate a DTM, a minimum value based on a certain number of point spacings. I want to make that about 5 in this case. So it'll be a slightly lower resolution model. And again, we'll filter to remove all of our points but our ground points. Click OK. And we're generating, again, a DTM, an elevation model. We can export this as a DEM file if necessary. Let's click OK. And it shouldn't take too long. It eventually will generate for us, filling in our gaps, because you can see there are some gaps in my model, and we can see underneath my point cloud, if I turn it off right now, our surface model. I'm not quite sure why this shader is doing what it is. Let me choose another shader. Let's use our color ramp shader. Again, we're getting a single color here, and I'm not entirely sure why. Maybe it's a good idea just to show a daylight shader. So what we're looking at now is not obviously an elevation, but just a textural model. once again, looking at this in 3D, this is now a raster layer. And it's a raster layer in which we've stripped out the points, leaving just ground. Now, at the start of my presentation, I mentioned that my objective was to begin with simple top-down drone images and ultimately generate some contours. And we're almost there. We've gone through several processes, initially analyzing our images. Now, granted, I didn't go through the entire process. That would have taken too long, but we pretended. Analyzing the images, generating the 3D point cloud. From that point cloud, applying classifications to recognize ground. We're almost there. The process of generating contours is very, very simple. We have a tool for doing that. We can define the contour interval. Let's set that at something a little bit less than 50 meters. Let's set it at 2 meters. You can obviously do whatever you want here. We can specify only a contour if necessary. We can generate areas. We can also find local depressions and local high points, or we can find our specific high point within this area. I'm going to do that. I'm going to create a spot elevation to show you where the maximum height value is in this area. All of these three-dimensional analysis functions that are now available to me were derived from the fact that our images were analyzed from multiple perspectives to generate this 3D data. So as a final step in this process, we'll go ahead and click OK, and hopefully we'll get some contours, as you can see. Probably a little bit too widely spaced, 2 meters, maybe 1 meter would have been better. But you can now see our contour lines that we can then export into whatever vector format we want. Google Mapper includes a range of export options, including shapefile, CAD files. So we'll export our data in maybe KML if we want to share it on a web platform. So a number of different formats for exporting those contour lines. And ultimately, that's how we can generate usable three-dimensional data from what originated as simple top-down drone images. I'd like to thank you for taking the time to watch my presentation. Hopefully you found it useful. Hopefully there's some value in it. I know a lot of the procedures were a little fast. I wanted to do something in real time rather than just going through PowerPoint. So you saw a simulation of how we can generate that data. Once again, thank you so much for inviting me to deliver the presentation, and thank you for taking the time to watch. Hopefully you found it useful.
Thanks, David. That was a great introduction to working with UAV data and the Pixels to Points tool in Global Mapper. I hope everyone attending the talk enjoyed it as much as I did. I'll be happy to answer any questions you may have. I look forward to speaking with you now.